Oi, self-improving diffusion models with synthetic data. Pretty cool paper here today. Most of the time, synthetic data, when it's used, just kind of destroys the actual model, right? If you're just naively training on it. They figured out a way here to actually, instead of training on synthetic data, to guide the model away from synthetic data, therefore away from the errors of the model itself, right? Super cool stuff. It also has downstream applications in terms of like they found ways to counteract bias in data sets. So let's get started. Disclaimer. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. So there's been a lot of hype around synthetic data, but the big finding, at least before we had this new O3 preview test time compute going on, was that naively using synthetic data, just like throwing it in there into the training corpus, did not go well, right? Um, it created autophagus, aka self-consuming loop, that can have a detrimental effect on performance. In the limit over many generations of training, the quality and or diversity of synthetic data would decrease in what has been termed model autophagy disorder. Autophagy? I don't know. MAD. I love that's MAD, right? But basically, that synthetic data is already imperfect, right? And so when you start adding the training data, you are training on further imperfections, and those imperfections compound and multiply, right? Because at the end of the day, it is not the real data distribution itself. It is still just an approximation of samples from that real data distribution, right? So those sources of error compound. Any approximation errors just iterate on themselves and get bigger and bigger, leading to poor performance and deterioration, right? And bias amplification. This paper develops self-improving diffusion models with synthetic data, which they abbreviate to SIMS. And basically, they take their base model's own synthetic data, and they have that to obtain a synthetic score function associated with synthetic data manifolds. And a lot of words, but they use their model's own synthetic data to provide negative guidance during the generation process, whereas previous attempts were providing positive guidance, aka just add the data to your actual training regime and go in the direction of that data the same way you would do so with regular data. Here they're saying actually, no, 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 don't encourage the model to go into the direction of synthetic data. Do the opposite. Have like the opposite gradients, negative incentive. Go in the direction away from your synthetic data. Tell the model whatever you're generating right now, go away from that. Leave that, right? But they're doing this simultaneously with giving the model regular data and saying go towards this, right? So the hope being that it's specifically the errors in the synthetic data that the model will move away from, right? So by doing so, they steer the model's generative process away from the non-ideal synthetic data manifold and towards the real data distribution. Here is a rough outline of the SIMS procedure, right? They use the base data set of real data to train the diffusion model using standard training, and then from that, they can get out the score function, which is just the model itself, right? The output. And then they use that new little model to create an internal synthetic data set by just having that new model generate a bunch of data. And then they take that base model and they do fine tune it a little bit using that synthetic data in the hopes that it actually degrades a little, right? To obtain this worse model, right? Then they use that worse model and their actual model pre crappy fine tuning to create their SIMS score function, right? Which is relatively simple. It's just a linear interpolation between the actual model and this fine tuned on synthetic data worse model, right? That's how they get their actual, the algorithm behind their SIMS score function, right? And then they take that algorithm, that process, and iterate it for 100 generations. Oh, sorry, to clarify. Then once they have this new score function, this actual new effectively model that is a combination of the other two models, and keep in mind, this combination, I said linear combination, by the way, it's a negation right here. So what you're doing actually is you're taking your real model and some percent of what it wants to do, and you're taking your messed up model and the 1 minus the original percent of what it wants to do, and you are subtracting, not adding the bad model, right? So you are hopefully removing error from the main model, and that gives you your end of the day final score function, right? And then you do that process, that algorithm, 100 generations, right? And because they did it for so many generations, they have now been able to basically show that there exists some guidance parameter, right? The percentage that we're gonna like interpolate between models, right? That omega, that W, such that no mad generation occurs. The model does not decay into insanity, basically. Now, this new technique is in contrast to previously proposed attempts to actually get synthetic data going, right? First being a fully synthetic loop in which each model, and like they just have generations of models, right? Where each one trains on exclusively on synthetic data sampled from models in the previous generation. Atrocious thing to do. Atrocious, right? But it's one example of a previous technique. Then there's the synthetic augmentation loop, in which each model in a given generation trains on a combination of actual real data and synthetic data from the last generation model. And then finally, a fresh data loop, in which relatively similar, except that every time the new generation trains on both real and synthetic data, that real data is fresh each time. They're actually holding out some part of the real data to be used on this next generation. And then this last one, this fresh data loop, I guess doesn't have the mad deterioration because the paper focuses in comparing against the first two loop types, the more traditional ones, right, which do experience deterioration. Let's talk some more specifics as to how this is actually done. So the size of a synthetic data set, of course, influences the effectiveness of this technique. As you make that data set, the synthetic one, larger and larger, and therefore use it more and more, then this technique would also collapse, right? But that's what you'd expect. That's just like using only synthetic data, right? Conversely, as you actually make that synthetic data set smaller and smaller, you end up not being able to properly estimate the error-prone distribution of the model, right? Giving you a result of pretty ineffective guidance, right? So if you don't create, when you're creating your synthetic data set upon which to fine-tune the model and create your bad model on, if you don't use enough data, then you actually will end up with a model that is not properly estimating all of the flaws in the main model, right? And therefore is not very useful in guiding the main model away from its own flaws. And experimentally, they find that choosing a synthetic dataset size that roughly matches the real dataset size works well in practice. And when they initialize this bad model, they do, of course, initialize it with the weights of the good model. And then, as I said earlier, they just train on the good model's own data to hopefully exacerbate some of the errors and get a good approximation of the errors in its data, right? Skipping ahead to the results, even a small negative guidance and a small amount of fine-tuning results in a Sims model that outperforms the base model. And for properly tuned guidance, improvement can be pretty substantial, with improvements in whatever metric they're using of like 30 to 55%. Pretty damn big. And this is really cool. Like they've found a technique by which they can actually estimate the errors of the model, exacerbate them a bit, and teach the model to avoid its own errors. Very cool stuff. Another thing that this may solve is that the data sets used for training AI models follow a distribution that differs from some desired target distribution. What they mean by this is the training data set you have doesn't actually perfectly reflect your test time data distribution, right? You're going to be tested on different stuff, either as the world changes or because the way your training data was sampled is just not perfect, right? Consequently, the synthetic data distribution generated by a model will also reflect this discrepancy. So your bad fine-tuned model, your error-prone model, will also have this same issue, even exacerbated, right? And they demonstrate that, they say they demonstrate it. Oh, in this section they will demonstrate it, I guess, that Sims can align the distribution of its generated images with an arbitrary in-domain target distribution that is distinct from the model's trained data distribution. So basically, potential to not only self-improve, but also mitigate extent biases in a base model. So what's happening here is the training data distribution is not quite aligned with your test time distribution, right? That's a source of error. When we create our bad Sims, what's it called? Our error prone model, right? Our especially error prone model with our fine tuning, we are also exacerbating those same errors. And then we point our main model away from that direction, right? So, what should hopefully happen here is that despite the fact that our training data is not perfect, is a bit different from our test time data, this method actually pushes the model away from our training data and therefore might mitigate biases that are inherent to the training data. Now, this experiment they do here, they have a data set that has 70,000 images of faces varying in gender, age, race, etc., with an almost equal split of male and female subjects, 51 to 49%, right? And then the actual pre-trained model, of course, generates a similar percentage of male versus female perceived faces, right? So that's all well and good. What they're going to do now is they're going to mess with the actual that data distribution by changing the percentage to 70% female and 30% male. So they took their data set and they said we're going to add in some bias into it. We're going to remove a bunch of the male face in the data set, and then we're going to construct that data set and use Sims to negatively guide our model away from this bias in the distribution. What they do is that they use that messed up data set as their part of their actual fine tuning to create a worse model. And then again, they negative guidance away from this worse data set, worse model, right? And they can create a data set that is once again whole at 50%. Meaning, if you suspect that your data set has some source of bias in there, such as a wrong percentage of male versus females in it, then you can artificially construct a data set that is in the reverse direction of bias just by like filtering out certain parts of the data, and then use that to steer your model back in the direction of a would-be perfect data set that you do not actually have. Now, in messing around with the actual guidance and data and everything, they did find that there is a what they call a prophylactic threshold on the ratio of the amount of synthetic data to the amount of real data that Sims can tolerate before it's incapable of fully preventing madness. So Sims, when done well, can prevent the madness, the deterioration of synthetic data, but if you use too much synthetic data, then it no longer has that ability, right? And this threshold is somewhere from 20 to 60% in the data sets they used of synthetic data to real data. But regardless, when you go above this threshold, it still does mitigate madness, even if it doesn't fully prevent it. So there is some ideal amount of synthetic data to use upon which you can fully remove madness. If you go above that amount of data, it still mitigates madness, but doesn't actually fully destroy it, right? Which is fine. But the problem being that as synthetic data continues to proliferate online, naive, unsupervised data collection will someday result in the amount of synthetic data exceeding the prophylactic threshold in standard training datasets and rendering methods like Sims less effective at preventing madness. So this is already a separate issue that they're pointing out here, is that in general, we're going to need better attempts at watermarking data, AI data, so that when it gets posted to the internet, that we actually know what it is and don't use it in the future, and better synthetic data detection methods. But they're just saying Sims is also susceptible to this issue. They also pointed out that future work should attempt to extend beyond diffusion models, and they even had the idea of what if, through interactions with the users and making synthetic data and collecting feedback, they could maybe even adjust a given model's distribution to align with user preferences. Which, interestingly, given this whole dichotomy of like, you actually need the opposite type of bias in a given data set to remove the type of bias that you want to remove, right? So what you'd actually be doing is you'd be curating data about what users do not prefer, as opposed to what they do prefer, which is pretty interesting. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.